Okay, can we start? Thank you all for joining us at this afternoon session. So the first lecture will be by Ronald Medicant. So Ronald, can you please start?
Okay, thank you, Bojan. Thank you very much to the organizers for this invitation. And also thank you very much to all my collaborators. Um, my talk is about circumstellar matter and disks in beta Lyra type binaries. I will present 3 new case studies that help to understand these interesting binary systems. First, I would like to present 3 different stages of binary evolution. The first stage is characterized by 2 stars inside their respective Roche lobes. The more massive star evolves first and fills its Roche lobe in this second stage of rapid mass transfer. In this occasion, the part of the atmosphere of this star is transferred onto the other star through the overflow of the Roche lobe of the donor star, and a mass ratio reversal happens. In the third stage of the binary evolution, the originally more massive stars turns to be the less massive star, but now it is more evolved than the companion. And the companion has accreted part of the mass of the other stars in the process. So 3 different stages of evolution of the binary system, a closed binary system, representing the stars that I will show in this presentation. We will name the more massive stars at present the gainer. In the past, was the less massive star. And the less massive star in the present time, we will name the donor star because it's transferring matter onto the gainer. Also, I would like to introduce the classification of light curve of eclipsing binaries. These light curves are usually named after some prototype system like Algol. The Algol type light curve present a flat orbital light curve between the consecutive eclipses. The beta Lyra type light curve present rounded shape of the part of the light curves between the main and secondary eclipses. And the W UMA type light curve present rounded, very rounded shape of the orbital light curve during the eclipses. So in this talk, I would like to talk about systems presenting beta Lyra type light curves that are characterized by mass transfer between the star and overflow of the Roche lobe of one of the components. First, let me introduce beta Lyra itself. It's a mass transfer system with a thick disk. The visual magnitude of this system is a multiple component system, but I would like to focus on the binary pair. The visual magnitude is 3.5 magnitude. The masses of the component are 13.16 solar masses and 2.97 solar masses. The temperatures are 30 kilokelvins and 13.3 kilokelvin, and the system has an age of 23 megayears. The orbital period of this binary is 12.9 days, increases at a rate of 19 seconds per year. So the orbital period is changing. The mass transfer rate in the beta Lyra binary is 2.2 times 10 to minus 5 solar masses per year. Relatively large mass transfer for these systems. and it presents an unexplained long periodicity of 275 days in the light curves in the photometry. Also, Vita Lyrae show enigmatic bipolar jets, material escaping from the orbital plane. For the first time it was possible to reproduce an image of the closed binary system using Vita Lyrae data obtained with the Chart Interferometric Array by Sao et al. In the 2008. And they produced this very nice movie of the system rotating every component around the center of mass. And you can see the distorted way, the distorted shape of the donor star. The distorted shape indicate that the donor is feeling the Roche law, influenced also by gravitational forces. Also, it's possible to interpret this movie in terms of the mass, the gas stream connecting one the star and the accretion disk around the other star. Some people, for instance, Skulski, in recent years, suggest that the donor is transferring mass onto the accretion disk around the gainer through magnetic field lines, because some evidence of magnetism is found in spectropolarimetric data of this system. Some of the questions on the evolution of Vita Lyrae type system are the following. What fraction of the transferred materials is lost from the system? We know that part of the material is being transferred between one component and the other one. But is all this material accreted by the gainer, or part of this material is lost from the binary? Another question is if the gainer is accelerated to critical velocity by transfer of angular momentum during the mass transfer. Petrovic et al. And the Ming suggest that the accretion stops at Keplerian rotation, but Popman and Narayan suggest that the star disk viscous coupling allows accretion near critical rotation. So we see that there are different prescriptions for the rotation of the gainer star, and it's not clear what happened. Another open question is how massive are the disks around the gainer in Vita Lyrae type binaries. It is very difficult to estimate from observation the mass of the disk. Another open question is, are Vita Lyrae disks of accretion-decretion type? Usually in cataclysmic variably, we observe accretion disk. In BE stars, on the other hand, we observe decretion disk. Wilson, in recent years, has developed a self-gravitating accretion-decretion disk model, very interesting. In the model of Wilson, the mass of the disk for Vita Lyrae is 0.04 times the mass of the gainer. Finally, another open question is what are the evolutionary progenitors and descendants of this system? For instance, Townsend and Charles this year proposed that some of these systems may be the progenitor of high mass X-ray binaries. In this context, it's interesting to show the discovery of double periodic variables we did some years ago, investigating the sample of BE stars in the Magellanic Cloud. We discovered a sample of stars showing beside the orbital period a long cycle. And more interestingly, we found a kind of correlation between the orbital period and the long cycle in this system. At present, we have more than 250 of these double periodic variables. In this graph, we show DPVs or double periodic variables in the large and small Magellanic Cloud, and also the galaxy, our galaxy. The orbital periods typically are between 1 and 100 days, and the long periods between 30 and 3,000 days. The graph, the lower graph show the ratio between the orbital period and the long cycle period. Is in the average 33, but with a relatively large scatter around this average value. So all these doubly periodic variables show beta Lyra type like curves. Beta Lyra is also a doubly periodic variable because of the long cycle. The class is summarizes in a summary paper long photometric cycle in hot Argos, published in the Serbian Astronomical Journal in year 2017. I would like to present here three new double periodic variables found in the direction of the galactic bulge. This is part of a thesis of one of my students in the master program of my university, and the paper is in preparation. In this graph, I show the long period versus the orbital period for these new 34 DPVs as red points, along with data for the previously known double periodic variables in our galaxy. And all of these stars are located very close to the center of the galaxy, characterized by galactic latitude and galactic longitude 0. The region here by the solid black line is the region explored by the Ogle project. All of these new DPVs are in the direction of the galactic center and are part of the catalog of Sosinski et al. Of binaries in the direction of the galactic bulge. One explanation for this long cycle comes from the theory of the magnetic dynamo model. In this model that we worked with my colleague Dr. Dominic Schleicher a few years ago, the rapid rotation of the donor, normally A-type, F-type giant, produce a magnetic dynamo with a length that is proportional to the orbital period. We need to remember that the donor is synchronized in rotation with the binary orbital period. So the prediction of this model that is in detail explained in the paper here predicts a long cycle proportional to the rotational or orbital cycle, and the constant of proportionality or the factor in this relation have to do with the nature or physical parameter of the donor, like luminosity, radius, and mass of the donor. And when comparing the model prediction versus the observed data is with pluses in this graph, and model data is with asterisks, we observe a relatively good match. So the dynamo model is interesting to explore like explanation for the long cycle in double periodic variables with beta Lyrae type like curves. I show here also another of our recent paper showing evidence of active regions in the donor of the Algol type binary B393 Scorpio. This evidence comes from the existence of metallic emission lines. These metallic emission lines are very weak. They come sometimes like single emission or sometimes like double emissions in the line of titanium to or iron to species. Also magnesium 2 lines appears with these characteristics. These lines are present in the raw data before any treatment of the data here, like cores in the absorption lines. And after removing the contribution of the donor, they can be presented more conspicuously, more clearly. And when following the radial velocity of these emission lines, we notice that they follow roughly the radial velocity of the donor. But sometimes the radial velocity of the donor in this graph is with a pink color. Sometimes the line follow a sinusoid very parallel or basically with some difference regarding the sinusoid followed by the center of mass of the donor. So the origin of location of the region producing these emission lines in metallic elements are probably or apparently located in some of the hemispheres of the donor star. Another point of evidence supporting the dynamo model comes from the theoretical support for winds driven by radiation of the hotspot. In the system, there is an accretion stream transferring matter from the donor onto the gainer. The stream impacts the gainer in the surface if no accretion disk is formed. But on the other hand, if accretion disk is formed, the stream impacts the disk and not the gainer. In both cases, a hotspot is produced, and the luminosity of the hotspot is proportional to the fourth power of its temperature. So hotter spots produce have a larger luminosity and can drive eventually a large wind. So this also is an additional support for the theory of the magnetic dynamo, of the theory that proposed that a mass accretion through the inner Lagrangian point variable is producing through change in the hotspot these winds that appear like the long cycle DPPs. DPPs are relatively massive. We show here some of them in red compared with normal algors. And the red points in the total mass versus the gainer mass diagram occupy a region with a total mass about 9 solar masses and with a gainer mass about 7 solar masses are relatively massive binaries. And this diagram is a rather more complex, showing the vertical axis, the fractional radius of the accretor, the gainer, in terms of the binary separation versus the mass ratio of the system. The region indicated here by the arrow, double arrow, indicate a region that is named tangential impact systems. So the system located in this region are hit by the stream in a tangential way. So they acquire a lot of angular momentum and could eventually speed up until critical velocity. In this diagram, we show with dots the semi-detached algors normal, not showing the DPV phenomenon, not showing the long cycle. With triangle, the disk of the double periodic variable system, and with cycle, the gainers of the double periodic variables. So in principle, apparently, the double periodic variables are tangential impact system, and they could eventually be rotating at critical velocities. 3 cases of study. One a system in the Large Magellanic Cloud, the other one in the bulge or in the direction of the bulge of our galaxy, and the other one is UU Cassiopeia. The first one has an orbital period of 7.7 days and a long cycle of 300 days. The second one, the orbital period is 24.8 days and the long cycle 800 days. And the third case is with an orbital period of 8.5 days and a long cycle of 270 days. First, for the first case, we have 12.5 years of data, and we have disentangled the light curve into a long cycle shown here in the upper graph and a orbital cycle shown here in the lower graphs. So we separated data in the ascending branch of the long cycle, the maximum of the long cycle, the descending branch, and the minimum of the long cycle. And we notice that the shape of the orbital light curve during the ascending branch, here in red points, is different from the shape of the light curve during the maximum of the light cycle, here shown as red point. And it's different also from the shape of the orbital light curve during the descending branch, and different of the shape of the light curve during the minimum. Please take notice or notice that during the minimum, the secondary eclipse disappears from the orbital light curve. This is very notable, very remarkable fact. And we also note here that during the ascending branch, the first quadrant here is brighter, but during the descending the descending branch, the second quadrant here is brighter, comparing with the other one. So some changes are observed and happening in the orbital light curve during the occurrence of the long cycle. We model with Goiko Jurassic and my collaborators in the light curve during the ascending, descending maximum and minimum of the long cycle. We model the orbital light curve that I remember was separated for the contribution of the long cycle light curve from using a disentangling code. And we found that the minimum is characterized, the minimum of the long cycle when the secondary eclipse disappears, is characterized by a very small disk or accretion disk compared with the other occasion during the long cycle. And this disk is hotter during the minimum of the long cycle. And the geometry and the relative contribution of these three components, donor, gainer, and disk, is shown here. And the sum, the total contribution, produce a disappearance or produce that the second eclipse disappears. Well, for this system, we found the temperature and the masses for the stars, also the radii, and the low G, and the orbital separation. And also, we observe that these chains can reproduce the chains in the orbital light curve. This temperature change from 7 kilokelvin to 4 kilokelvin, and this radius change from 7.5 to 15 solar radii. Another system is this one with 18.5 years of data, mainly from the Oakley database. And we analyze mainly here the I-band light curve. We show here the long cycle is clearly visible in this dataset. And we make a zoom in the upper graph of one of these regions, noticing the consecutive occurrence of the primary and the secondary eclipse, the primary and the secondary eclipse. Yeah, this is a very interesting system. In visual data, we have fewer data points. And here I chose some phases orbital light curve, but for different strings of data. So the colors here indicate a string of consecutive data. And what I want to show here is that for a string of data, there are changes in the relative depth of the eclipses. For instance, in this string of blue, light blue color, the secondary eclipse is deeper than the main eclipse. But in this string of green colors, the secondary eclipse is shallower compared with the main eclipse. Also, a wavelet analysis of the world dataset show the long cycle periodicity very well. It's a cycle length of about 800 days, but changing during the time. And another thing here very interesting are the data colors here indicate different range of heliocentric Julian days. The main eclipse is not so variable like the secondary eclipse. The secondary eclipse, when we have the disk facing us, show the larger scatter, not so the primary eclipse. The same system, we observe here the long cycle. With different color, we indicate the different orbital phases. And the solid lines show the fit we did for showing the long cycle and remove the long cycle and work with receivers. But what is interesting here is that the main eclipse characterized by color blue and red seem to be decreasing in I-band magnitude. On the contrary, the secondary eclipse characterized here by the color green seem to be increasing in brightness. Mhm. And these tendencies are reproduced by these fits in this diagram. The magnitude of the primary eclipse decreases and the magnitude of the secondary increases. These are secular chains in timing scale of decades that, together with the variability of the long cycle in time scale around 800 days and the orbital time scale of 24 days, composes three different time scales of variability for this noble periodic variable. We took two extreme examples of light curves when the secondary and the primary eclipse change the relative depth and model it with our accretion disk model. And we observe that the disk is thicker and larger in this occasion, and is thinner and smaller in this occasion. So in other words, when the secondary eclipse is deeper, what is happening is that we are observing a disk thicker and larger, and this configuration produce the observed secondary eclipse more deeper. Finally, I want to show the UE Cassiopeia analysis, considering almost a century of photometric data from different sources. We obtain a new orbital period for this binary, but interestingly, we also detect a long cycle in the I-band data of 270 days. And when we face the I-band data with this long cycle phase, we obtain this light curve that I show here. So this is relatively new result. And also when facing the integral photometry with the orbital phase, we observe not only the general tendency shown here by the red line, but also some drops of magnitude that are very characteristic for this system. And the world population of data, the world data set can be modeled. We do two Gaussians of different width. So the first Gaussian indicate the distribution of point around the main tendency of red line here, and the other wider Gaussian indicate the distribution of point of event of drops of magnitude. And these drops of magnitude are not only located in the integral visual band photometry, but also in the ASAS and photometry, in the visual band and the G band. So, and the UE Cassiopeia also present a variable disk. When comparing 6 different data sets, the models, we obtain a disk radius changing from 22 to 18 solar radii, the vertical thickness changing from 4 to 9, the inner vertical thickness to 6 to 10 solar radii, and the disk outer edge temperature more or less constant, about 16,000 Kelvin. The hot spot is changing from 36 to 70 hotter than the disk, and the bright spot from 24 to 50 hotter than the disk. We observe in many DPVs that the hotspot position is relatively unchanged, but not the bright spot position that is changing a lot at different parts of the accretion disk. Mhm. And the position of this star in the infrared color diagram is along with other binaries of systems containing circumstellar matter. These are the normal giant and normal main sequence, the star single, and the pluses indicate BE star and the open cycle double periodic variables. And the red dot is U Cassiopeia, indicating in its position the existence of circumstellar matter. Main result for this system is improved orbital period and plus long cycle. Detection, the orbital separation is 52 solar reading, is a pair of 2B type star, early type, 22 and 30 kilokelvin, 9 plus 17 solar masses. Also, we obtain the reading and log G of indicating a giant plus a dwarf for this UU Cassiopeia system, a variable equation disk, and an enigmatic obscuration event. The task summary is the long cycle in some beta Lyra type binaries are still an unexplained phenomenon, but variable mass transfer affecting the disk and spot probably plays a role in them. UU Cassiopeia long cycle is detected at the I-band and needs confirmation. UU Cassiopeia may be a relatively massive double periodic variable. These in some double periodic variables are clearly variable. This suggests variable mass transfer. Additional indication that the bright spot, not the hot spot, is very variable in this object. What is the origin of this spot and its variability? Modulating mass transfer may explain the long DPV cycle and variable spot, for instance, through the dynamo model. And finally, enigmatic obscuration event in UU Cassiopeia were detected. Thank you for your attention, and thank you also for all collaboration, some projects, and many thanks to the organizers again.
Thank you, Ronald. We are late, but I will allow one short question, if there is one. I don't see anyone, so okay, there is one from Tomislav. Is there any dust formation? Ronald, sorry, you're muted.
Sorry. Now I respond the question. Apparently, there is no dust because the infrared photometry, WISE, for instance, indicate a color excess, but more compatible with the tended circumstellar envelope, like in B star. But we don't see in the infrared photometry evidence for dust in this system.
Thank you. Let's proceed. I will ask Snezhana Stanimirovic to step in. Snezhana is our former student. Hi, Snezhana.
Hello. Okay, can you see my presentation?
Yes, okay, it's gone.
Okay, can I go, Brian? All right.
Yeah, sure.
Hello, everyone. It's wonderful to be here in this very special virtual space. And I am going to take us to slightly larger spatial scales, so parsecs, kiloparsecs. And I want to focus on the neutral interstellar medium in the Milky Way and nearby galaxies. And so you will see in this talk, I will be switching between the Milky Way and nearby galaxies quite often. Hopefully this will not be just to confuse you, but I really want to stress a very important point that we live in a sort of a very interesting and complex time when we can basically start doing very interesting science that for many, many years we were able to do only in the Milky Way, but now we can do that in the nearby galaxies And that's really important because nearby galaxies offer a much broader parameter space in terms of interstellar radiation field, metallicity, all sorts of environmental constraints. And that's extremely crucial for testing our theories for the interstellar medium in general. So just to kind of start with the background, we all know that the neutral atomic gas plays a very interesting role in terms of global evolution of galaxies. And it's sort of centered in between hot and warm ionized medium and colder and denser molecular gas. And typically in galaxies like the Milky Way, in terms of gas distribution, neutral gas dominates. We also know that molecules such as molecular hydrogen form out of the cold neutral medium on the surfaces of dust grains. And so therefore, that neutral gas or predominantly atomic gas is extremely important for starting seeds of star formation. And eventually, during the lifetime of predominantly atomic diffuse clouds, something would happen, say clouds would collide, or lots of other interesting processes that we still don't fully understand would drive phase transformation, and essentially those predominantly atomic clouds will become denser and colder regions where molecules start to form, and we end up having molecular clouds, which also have a lot of dust. And this is nicely shown in this middle picture provided by the Planck satellite. Molecular clouds are places where everywhere in the universe we see star formation, and that of course leads to planet formation and a lot of interesting things happening even closer to home. But we also know that throughout their lifetime, through stellar winds, through photoionization, and later on through supernova explosions, stars extremely influence and affect that neutral gas through interstellar turbulence and through a bunch of different processes that we like to call stellar feedback. So it's an interesting ecosystem with feedback loops. Over the last 10 years or so, we have seen beautiful observations from the Milky Way, and I'll show you in a moment other galaxies, which are really zooming in at very high resolution at the diffuse interstellar gas, or the predominantly neutral gas in galaxies like the Milky Way. So this image comes from the Arecibo telescope and has an angular resolution of 4 arc-minutes. This is a Gulf H1 collaboration. This is actually a movie and I can play this. So effectively I'm showing 3 different images obtained at 3 different radial velocities. It's slightly different color just to kind of show you the depth of hydrogen emission. So this is emission from atomic hydrogen at the wavelength of 21 centimeters. So you can see a ton of interesting and really complex structure. Of course, we want to understand what leads to that interesting structure formation. So let me move on and show you another beautiful picture, which is 21 centimeter line emission from the Small Magellanic Cloud, one of our closest neighbors. And this image was obtained with a very new telescope in Australia. This telescope is called ASCAP. And so this particular image was obtained essentially with only 1/3 of the interferometer. So this was commissioning early time, and we were still trying to figure out is the telescope working well or not. So already at that stage, this was at much better sensitivity and better angular resolution than what we have had for the several previous decades. So this is again showing emission at 3 different colors, just to emphasize depth and diversity of structures. So why is this so interesting? So basically we want to understand physical properties of neutral gas in galaxies like the Milky Way and the SMC. So we want to understand the morphology, but we also want to understand the range of densities and temperatures that galaxies have, because this is important for galaxy evolution and important for star formation. And over the last 10, 20 years, numerical simulations have really provided powerful ways of studying this interstellar medium by having the ability to turn on and off individual physical processes. And numerical simulations are telling us that stellar feedback plays a crucial role in understanding galaxy evolution and properties of the interstellar medium. For example, this work by Philip Hopkins and his group at Caltech shows that in order to explain fluffy morphology we see in galaxies, we need to include stellar feedback. So we need to include radiative momentum, we need to include supernovae. Furthermore, when simulations look at galaxies with or without stellar feedback, if they don't include stellar feedback and if they try to plot essentially a histogram of gas density that's shown on the bottom panel, they get this dotted line, which is telling us that without stellar feedback, simulated galaxies have way too much dense gas, and that leads to a runaway star formation and produces galaxies with a huge star formation rate and things we do not observe in real galaxies. So once they start including individual feedback channels, individual feedback processes, they get down to something that's shown in red and blue, which is a lot more realistic to what we observe. However, right now, one of the key uncertainty in numerical simulations is what kind of feedback channels are more important, and specifically on which scales they predominantly operate. So we really would love to constrain that observationally. So in this talk, I would like to focus on, am I doing time bias? Yeah. So in this talk, I would like to focus on 3 different topics. So one is the thermodynamics and constraining excitation temperature of that neutral gas. And then that will lead me into the topic of shielding of molecules in the predominantly diffuse neutral gas. And at the end, I want to say a few words about stellar feedback and how we can, with the new observations and high spatial dynamic gradient observations, constrain feedback. So in terms of thermal structure, when we think about the Milky Way, and specifically any galaxy at roughly solar metallicity, and consider heating and cooling processes, various heating and cooling processes, we like to plot that as a thermal pressure as a function of density. So I'm really focusing on that top right-hand panel. And you see a black line, which is theoretical line showing us essentially equilibrium conditions, so conditions where heating equals cooling rates. The dots here in color come from numerical simulations. Essentially, numerical simulations without much included turbulence agree with analytical theoretical solutions that we would expect to see neutral gas to congregate at 2 different temperature regimes. This is what we call the cold neutral medium, CNM, and the warm neutral medium. The land in between is supposed to be thermally unstable, and any parcel of gas that lands there should very quickly migrate to one of the 2 directions. However, if the medium has a lot more turbulence, that land will be a lot more populated. So I'm also showing here a bunch of colorful diagrams which are telling us conditions, density and temperature conditions in which we can have multi-phase gas, that's CNM and WNM in galaxies. And of course, because heating and cooling processes depend on UV field, they depend on the metallicity, these diagrams have metallicity as a y-axis and thermal pressure on the x-axis. And that multi-phase region is shown in gray. And just as a snapshot, you can see that if we change interstellar conditions, if we change radiation field, if we change the metallicity, the conditions for existence of the multi-phase medium should change. And of course, this is what we want to test in the observations. So another way I can show that pressure diagram is by just looking at the histogram of gas, neutral gas as a function of excitation temperature. So on the right-hand side, here is my cold neutral medium and the warm neutral medium. Observationally, to measure this, we need to do absorption line measurements. So we typically use 21 centimeter line. We look in the direction of background sources. And for many years, we were able to very well constrain the excitation temperature of the cold neutral medium, because cold neutral medium has high optical depth, so it's easy to measure. So when you look at this, observations and theories sort of agree. One thing you notice right away is that observations are missing anything essentially warmer than about 100 Kelvin, and that's where we expect the warm neutral medium to be. So warm neutral medium has a low optical depth. To detect it in absorption, we are really looking at essentially line wings, so very, very weak absorption lines, and those are hard to obtain. They require a lot of observing time. So in order to constrain that warm neutral medium, very recently my students and I used a very large array in New Mexico, or a Carl Jansky very large array. And we looked in the direction of 57 background sources and obtained extremely deep hydrogen absorption spectra. So this is a noise level at like 10 to the minus 4, 10 to the minus 3. So it's a really deep. So on the right-hand side, you can see the distribution of our sources. We like to get away from the plane of the Milky Way because that's where we can do our job of temperature estimate much better. It's the line of sight is cleaner. And we also teamed up with a group from Princeton that gave us thousands and thousands of synthetic spectra, and we use that to constrain our observational methods, because there we know what the temperature answer should be. So it's really important to constrain our observational biases. So let me show you our one of our results. So this is on the right-hand side, the theoretical histogram, what we expect to see. This is in gray, what we got after 600 hours of VLA telescope time. We call this project 21 sponge because we were sponging away any unused gaps in the telescope schedule. So, you know, give us 5 minutes here, 10 minutes there, we'll take it and accumulate. So from here, we were able to constrain by mass the fraction of atomic hydrogen in the Milky Way as a cold gas, temperature less than 100 Kelvin, that's 30%. We constrained that middle end of thermally unstable gas to about less than 20%. And then everything else is essentially warm neutral medium. But the tricky part is, even though we were sensitive to temperatures up to 4,000 Kelvin, we have very few detections at the temperature above 1,000 Kelvin. So why is this? Where is that warm neutral medium? Why can we not see it nicely in absorption? So after some painful stacking analysis, we could finally see it. And this tells us that that warm neutral medium has a temperature of 7,000 Kelvin. And in order to explain that temperature, we need to introduce a secondary method for the excitation of the 21 centimeter line. And that's, so the first method is called collisions with particles, hydrogen atoms, hydrogen molecules. But the second method is with the Lyman alpha absorption. So when a hydrogen atom absorbs the Lyman alpha photon, gets excited, then gets de-excited every once in a while. After the de-excitation process, the hydrogen atom will land in that excited hyperfine state, and that will produce a photon at a wavelength of 21 centimeters. So yeah, so this effect is called the White-Hausen field effect, and sort of our work shows that this is very important in the Milky Way, and it's still very poorly constrained. And effectively, we are suggesting that numerical simulations are doing okay, but they need to move the peak of that warm neutral medium more to the right, because that warm neutral medium, because of a higher pool, larger pool of Lyman alpha photons, is actually more important. Okay, so yeah, we're starting to do similar work in nearby galaxies. Here is an example of the Small Magellan Cloud. And this was done with the Australia Telescope Compact Array before ASCAP, and it took about 800 hours of telescope time to look in the direction of 50 or so background sources behind a Small Magellan Cloud, and then play essentially the same game to try to figure out the temperature. The SMC is so interesting because it has metallicity 10 times lower than the solar metallicity. And this is where heating cooling processes are very different. We expect to find different temperature for the gas, for the cold neutral medium and warm neutral medium. So we are getting there. ASCAP was essentially built to be able to do this work much, much faster. And a lot of this work is happening already and will happen in the near future. So I will move on now. And so the 21 Sponge project gave us information in about 60 directions in the Milky Way, which mainly sample diffuse gas. So it's like a low column density gas. But along those directions, we have really incredibly well, incredibly well diagnosed properties of neutral gas. So we have information about the kinetic temperature. We have information about the column density. We have information about thermally unstable fraction of gas and the level of turbulence. And so one of the questions we wanted to ask is what's happening with molecule formation in these diffuse regions? And so typically, when people study molecules, they go to dense regions, high optical depth regions, high extinction regions. And there you find tracers like HCN, you have water, ammonia, all sorts of different molecular species. However, for many years, in random directions in the Milky Way, which have a much, much lower gas density, various molecular species have been observed with abundances that are extremely off anything that classical equilibrium models predict. So there's a lot of non-equilibrium happening in these diffuse regions. And basically we used the ALMA telescope, and in the direction of about 25 of our sources looked for 4 different molecules. HCO plus, which is essentially a precursor on the way to making carbon monoxide. And then HCN and HNC and CCH, which are essentially considered as high density tracers, and they're typically found at in high density environments. So here is just an example of 2 of our sources. And in the bottom panel, you see hydrogen absorption. So effectively, those 2 directions, they both have cold neutral medium, which is the seed for making molecular hydrogen and other molecules. So they have a ton of cold neutral medium, but you can see that in terms of their molecular abundancy, they're extremely different. So 3C13A direction has essentially no other molecules, that we can detect, while 3C111 is abundant to the point that lots of these species are saturated and we don't know how to deal with them. So this is work by my graduate student, Daniel Robarczyk. And so one of the things we have done is to look at a total column density of hydrogen that we have from 21 Sponge and plot that as a function of column density of these different molecular species. And one thing you can notice right away is that at low column densities, there are no molecules. And once we sort of hit 2 times 10 to the 21 hydrogen particles per square centimeter, suddenly the molecular abundances of all these different species goes up. So you can see this rise in molecular abundance. So what this is telling us is that the key thing for molecule survival is shielding. So what we need to have is a long enough column of gas, which means a lot of hydrogen atoms. Hydrogen is mixed with dust grains. And it's the dust along that line of sight that does the shielding by absorbing radiation, warming up, and then re-emitting in infrared, and effectively saves molecules from dissociation. So this is, so as far as we are aware, this is a sort of a nice example and the first example where we see this clearly for these different species. This has been known, the shielding has been known to play an extremely important role for molecular hydrogen. And just as an example, I have here Perseus molecular cloud. These are Herschel observations, a lot of interesting star forming regions as well as dark cores. And by being able to use high resolution observations, we were able to plot H2 fraction as a function of total gas column density on the left-hand side. So these are real observations in black, and then model predictions in red. So you see it's exactly the same thing. So when you have a low gas column density, there's essentially no H2. Once you hit that perfect column that's enough to shield and help H2 survive, suddenly abundance of molecular hydrogen rises drastically. And this really agrees very well with the theory. These are theoretical models going all the way back to Spitzer 75, and then also there are more recent models that take things into consideration. So yeah, we can do that very well in the Milky Way, where we can resolve individual regions, and we can also look at diffuse regions. So far, for nearby galaxies, we were able to just work with random directions. And this is H2 from fuse as a function of total gas column density for the large Magellanic Cloud and the small Magellanic Cloud. And the bottom line is that things are reasonably okay, but we clearly have problems at low metallicity. So low metallicity galaxies where shielding requires much larger column of gas are still not understood theoretically well. So this is something where future work with future high resolution work will really help us constrain what's happening at low metallicity. So for the last part of my talk, I just want to focus on this stellar feedback. So stellar feedback, supernovae, stellar winds cause interstellar turbulence, and turbulence affects structure in the interstellar medium. It also affects very much molecule formation. And so we've been trying to play the game where if we can study kinematics and structure of neutral gas, can we actually go back constrained level of turbulence, and can we use that to really pinpoint those different channels of stellar feedback and say on which scales they operate, what's really important where, so that then we can guide numerical simulations. So one of the games we play when studying interstellar turbulence is using something that's called a spatial power spectrum. So I'm showing here neutral hydrogen observations of the SMC and the LMC in color. And what we typically do is we take a whole image, these are typically column density images of atomic hydrogen, we do a Fourier transform and then plot essentially power in the image as a function of spatial scale. So this is the spatial power spectrum. And if the structure is dominated by turbulence, the spatial power spectrum has a power law, a nice power law behavior, and the slope of that power spectrum is telling us something about the type of turbulence. Is the turbulence driven by shocks, or is the turbulence driven by say, large-scale gravitational motions, like large-scale stirring motions? For the LMC, things get a little bit more complex because the LMC has a disk, it's a disk galaxy. And so there's a break in the power spectrum that corresponds to the transition between a 2D turbulence, which is within the disk of the LMC, and then everywhere else, which is a sort of a more three-dimensional turbulent motions. So we need to pay attention to that, but it's an interesting, geometrically an interesting point to consider. One thing that's been puzzling for many years when people have looked at other galaxies, if we think that stellar feedback drives turbulence, we should expect to see that galaxies with a higher level of star formation should have a different power spectrum. But that has not been the case. Effectively, power spectrum information from other galaxies that's typically measured on kiloparsec scales has given really only scatter points, scatter diagrams. So this is not something is either weird or it's really the resolution that's affecting results. So now with ESCAP, we can reach down in terms of SMC and LMC to really scales of individual clouds, and this is extremely powerful. So now instead of taking a whole galaxy image to calculate that single power spectrum, I can play a game and take a small portion of the image, calculate the power spectrum, write down the slope, and then keep moving across my image to effectively map spatially what's happening with the slope of the power spectrum as we hit individual different regions across the galaxy. And so this is the result. So for the SMC, again, so I'm now plotting the slope of the power spectrum, that index n, and every pixel in this image represents the slope value. Effectively for the SMC, we have convinced ourselves that we don't see much diversity. So basically, we see uniform turbulent properties. Basically, statistically speaking, we cannot distinguish between orange and light yellow right now. And that's a very interesting result. So it could be driven by metallicity, it could be large line of sight. We can talk about that later if you have questions. But the LMC is much bigger and provides a lot more diversity. It has this whopping 30 Dorado star-forming region. So let's see what happens there. And let me show you, because the LMC has that break in the power spectrum, I now make two images. The small scale slope M on the right side. The left hand image shows the large scale slope N. And you can right away see that the colors have exploded. There's a lot more diversity, there's a lot more interesting information. And I'll just highlight that this work was done by two undergraduate students, Sam and Dell, in my department. So what's happening? So let's look at the small scales first. Around 30 Dorados and several star-forming regions, we are seeing sudden steepening of the power spectrum slope around those star forming regions, intense star formation regions. So basically, if I have a power spectrum and I have that kind of looks like this, and I have some small clouds, say giant molecular clouds sitting here, as the star formation happens, it photoionizes those clouds, essentially, evaporates them, turning dense molecular gas into more warmer and diffused medium, which would effectively steepen the power spectrum. And this is exactly what we are seeing kind of in action on very small scales right around the sites of star formation. And some numerical simulations have predicted that that should happen. So this is a work by Gritsdale et al., where if you have a power spectrum before including in simulations feedback, once you include stellar feedback, everything steepens. So small scale structure clouds get destroyed and turned into more diffuse medium. So this is nice. So basically we're seeing how stellar feedback modifies locally the power spectrum on small scales right around key sites of star formation. And then on large scales, there's also a lot of interesting stuff happening, especially in the outskirts. We see those long elongated features with the red color and orange color, and that means, again, a steep power spectrum slope. And what we think is happening is that we are seeing flaring of the LMC disk. So within the disk, the turbulent motions are sort of constrained to 2D. And then once you hit the flare, the scale height suddenly increases, and then the turbulent motions become 3D. So this has been predicted by numerical simulations, and it's nice that we are seeing that for the first time in each one. So here are my conclusions. The bottom line is we are really starting to do a lot of ISM work, which traditionally was being done only in the Milky Way nearby galaxies and at high resolution, and that's super important for testing sort of extreme parameter space of metallicity and interstellar radiation field. Shielding is extremely important for molecular survival, and we can map turbulent variations of turbulent properties across individual galaxies, and a lot more work will come in the future from radio telescopes like ESCAP, like the Square Kilometer Array, Meerkat in South Africa, and Next Generation VLA. Thank you very much.
Okay, thank you, Snezana, for a very nice talk. Any question? Okay, so it's not necessary to raise hand. If anybody has any question, he or she can just ask. Okay, if no. Okay, thank you, Snezana. Thank you once again. And we will move on to our next speaker. It's Thomas Panutti. Hi, Tom. Can you hear us?
Can you hear me now? I
Yes.
can hear you.
Okay, we can hear you now. So
Great.
please go on with your presentation.
Okay, thank you very much. Hello, everybody. My name is Thomas Panuti. I am at the Morehead State University in Kentucky, and my talk today is spectroscopic and hydrodynamic analysis of the northwestern rim of the galactic supernova remnant G156.2 plus 5.7, or how an unfortunately located background cluster of galaxies can really ruin your day. Okay, so first of all, thank you to the invitation to give this talk. I appreciate this. It's great to see people and hear people again. And I hope everyone's, in all these circumstances, everyone's families and loved ones are staying safe with everything. So what I'll be talking about today is some of the modeling analysis I've been doing on this peculiar galactic remnant G156.2. I will also be talking about another remnant, CTB1, which I've had some traction in the analysis of that object lately, and I'd like to discuss the results for that as well. So this work is presented with my Glenn Allen, my former postdoc supervisor, and also Roland Kothis, who has also recently come on board the project and has contributed radio data to this analysis as well. So the science goals of this project, this goes back to the first initial work with this galactic remnants, which I did in the X-ray back when I was a first postdoc, was trying to understand the highest energy X-ray emission from galactic supernova remnants, the relationship between this emission and cosmic ray acceleration by galactic remnants here too. And as you can see here, one of the legacies of the Chandra X-ray Observatory with its high angular resolution is the detection of filaments along the perimeters of these remnants over here, which spectroscopic analysis shows that these are not, the emission mechanism for these filaments is not thermal emission, which is the canonical emission mechanism for supernova remnants, but instead synchrotron emission. These would be actually X-ray emission from cosmic ray electrons accelerated to extremely high energies. So one of the legacies, of course, for the Chandra Observatory is realizing that in remnants like the Tycho remnant, which is pictured here, that you actually could see filaments of emission, which is actually located on the perimeters here, showing that these sources are, their regions of acceleration are localized to narrow regions along the leading edge of the remnant here too. So a legacy, of course, would be to try to understand how these remnants can accelerate particles, cosmic ray electrons, up to, say, the knee energy of the cosmic ray spectrum. Supernova remnants are thought to accelerate up to that energy, but evidence of catching these remnants in the act, if you will, of showing that they're producing this emission still remains lacking. So once we can detect this emission, another question becomes the distribution of the energies of these highest energy particles here. Can you model these with a standard Maxwell-Boltzmann velocity distribution, or do you need another alternative distribution to determine this? Knowing the distribution of these electrons themselves actually has input into how these particles are accelerated and has important bearing from there. So in the course of our studies for this here, we were doing research on remnants which had a reported hard component to the X-ray emission. And this remnant G156.2 plus 5.7 was one of the ones which we considered. This remnant has a distinction of being the first galactic remnant that was detected by its X-ray emission, by a ROSET observation, and then was actually confirmed to be a remnant by a radio observation. Most remnants have been detected in the radio with a complementary X-ray emission following. So this remnant actually went counter to that trend. It's enormous on the sky, 110 arc minutes. So you're looking at approximately nearly 4 times the angular diameter of the full moon. The distance of this remnant has been a source of some controversy. It was once argued that the remnant may be as close as 300 parsecs based on an absorption feature seen toward its southern rim, which I'll be discussing shortly. But the more recent analysis has really established that it must be at least 1.7 kiloparsecs based on direct observations of proper motion expansion. In the optical, this is the optical picture which is shown over here. We actually have a filamentary structure, which you can see for diffuse patches, but these filaments, which you see on the edges, pretty nicely match the radio rims of the remnant pretty well. So we have it's a complex emission in the optical where we have not just the filaments on the perimeter, but also on the edges and the extreme here too. And finally, the radio properties of this remnant, despite its large size, it's still extremely weak in the radio. Integrate overall is all size, its angular extent here, is only about 5 Janskis at 1 gigahertz. And a measurement of its surface brightness, it makes it one of the lowest known of all remnants. This comparison was made back in 1992. To the best of my knowledge, there hasn't been a remnant which has demonstrated even lower surface brightness. But what's making this remnant peculiar is it's X-ray luminous, but really weak in the radio. That was something really kind of stood out from its first detection. Yes, Roland Kothis has recently come on board this project here. He's providing a new radio data for this remnant. So this actually is showing for the ROSAT PSPC image over here on the left panel with the radio contours overlaid. What you can see here is that the remnant is the radio emission is localized to just a bright southern rim, which is weak or absent in the X-ray, and the northern rim, which is quite prominent in the X-ray and the radio. So it's naturally to kind of draw attention to this location over here. And a zoom, which is shown in the right panel of this X-ray emission over here, shows actually, as you zoom in, to our surprise, the radio emission actually extends beyond the angular extent of the X-ray. And while this was noticed here in the radio, in the first ROSAT images here, higher resolution X-ray observations made with the XMM have confirmed that surprisingly, the remnant extends by a significant amount in the radio compared to its X-ray perimeter. These black boxes, which I show here, show regions of spectral extraction, which we had for the archival XMM Newton data here. This is an outer rim and an inner rim, and our interest was actually trying to compare the spectral properties of these sources here. Okay, so the X-ray properties of the remnant here. 10 to 35 ergs per second. This actually places it toward the higher end of the luminosity function of the X-ray emission from galactic remnants, which again is a remarkable contrast to the fact that it is so radio weak in its emission here. The initial X-ray spectral analysis here found that it was going to be 2 components of X-ray emission were needed to actually fit its emission properly. And that's unusual as remnants go. Most of them, especially remnants with an involved age like this one here, are thought to have come to an equilibrium of 1 temperature here. But you actually would have a standard thermal component of about 0.5 keV here. But you'd also have a second component which you could fit with either a thermal temperature of 8 keV, which is not possible, not physically realistic for supernova remnants, or a power law of 2.1. And that power law of 2.1 is very consistent with synchrotron origin. So in the years after its discovery, this remnant attracted attention as possibly being one of the small handful of remnants which actually have an appreciable hard X-ray emission to its X-ray hard emission to a component to its X-ray emission. These would make this remnant really kind of stand out as an excellent laboratory for the acceleration of cosmic ray particles. By analyzing the spectrum, by fitting that hard component, we can actually see it makes the best candidate for actually trying to analyze how remnants emit or accelerate electrons to cosmic, to relativistic energies here. So the hard emission, the subsequent observations localize this X-ray emission to the northwestern rim. It's because this rim is also radio bright, and radio, for the large majority of supernova remnants, the radio emission is actually going to be synchrotron. This becomes a very attractive site for analysis, where we can actually use synchrotron models based on which are constrained by direct radio observations to understand the X-ray emission from this remnant, to understand the hard component of the X-ray emission from this remnant as we observe it. Okay, so the analysis was proceeding in trying to understand this component here. And what we had done, the ambitious project we had here, was to try to jointly analyze X-ray emission from this remnant from the ROSAT PSPC, the XMM Newton EPIC cameras, and the ARC-C PCA. This would give us coverage from about 0.2 to 12 keV of the whole remnant here, of that rim, which would do a lot to constrain any kind of hard X-ray emission that we could expect from this location here. The challenges that you'd have here would be to address the differences in the capabilities of the instruments. Especially one challenge we had here, which I'll be discussing shortly, is the fact that we would have such so many discrete X-ray sources found in the field of view. We use the RXTE PCA because it would give us the serendipitous coverage into higher energies. The ARC-CE, of course, was designed primarily as a timing instrument, but its coverage to higher X-ray energies allowed it to be used as a way to detect harder X-ray emission from sources such as the galactic remnants like G347, Vela Junior, SN 1006, all of those remnants which actually have a hard X-ray synchrotron component. So while the PCA would have that energy coverage beyond what you would have for Chandra or XMM Newton while the ARC-CE was still active, its drawback was it had an enormous field of view with no spatial resolution capabilities. So any kind of observations or analysis of the ARC-CE data must take into account any other serendipitously observed sources, along with the source of the emission from the northwest rim, which is what we want to localize in the case of G156. And so this is how the unfortunately located background cluster of galaxies can really ruin your day. In an image which I'll show you shortly of the northwestern rim, Yamauchi et al. Described the X-ray properties of a background cluster of galaxies seen right on the rim here. And it appears that the X-ray spectra here could be fit with a standard thermal model. The redshift of 0.16 implied how far this away here is. So what was argued by Uchida was that the hard X-ray analysis of Suzaku spectra of this remnant here was that the hard X-ray emission detected from this rim was not due to the remnant itself, but instead was due to this background cluster of galaxies here, which was just simply located along the rim. And we had, therefore, I'll show you in the upcoming slides, the location of this cluster here. So this was another component, another complication we had to consider in trying to analyze the X-ray emission from this northwestern rim. This image here shows exactly the challenges we had in trying to, again, with the ARC-CE PCA, the advantage would be giving us a greater energy coverage to harder X-ray energies, but the drawback, of course, would be that there'd be other sources detected. This is showing the location of that cluster, 2XMM over here, but you'd also have over here at the side a radio galaxy, 3C130, which has X-ray emission not only due to the galaxy itself, but also extended emission due to the X-ray cluster to which it belongs. You would also have up on the north rim over here, AXJ0500, another hard X-ray source, which is actually known in the ROSAT and OSCA observations of this remnant here, which was once believed to maybe be the pulsar, a neutron star associated with this remnant here. It was an additional X-ray spectral analysis indicates the column density toward this was greater than the column density toward the remnant. So it was argued that this was not actually physically associated with the remnant. It was instead more likely to be a background galaxy, just serendipitously located. But you could see here the challenge then becomes that in the PCA field of view, shown by this cyan circle over here, you have not just the northwestern rim emission that you want to analyze for the remnant, but you also have the cluster, this hard X-ray source, and this radio galaxy, and its diffuse emission. So this becomes a complication in the analysis. This other cyan circle here shows it was another ARC-CE observation made of the southern rim, the southern part of the remnant, as a way to try to understand the hard X-ray emission produced by the whole remnant here. The southern rim here are our X-ray analysis of the southern rim here proved that this was just simply a standard soft X-ray emission. There was no hard X-ray emission detected. These other letters here, labeled sources A, B, C, and D, these are all simply stellar sources, galactic stars, which are seen just in serendipitous line of sight. They did not produce appreciable emissions, so their contributions could be to this analysis could be safely ignored. Okay. These images show here the locations of the spectral extraction that we performed. This upper panel up over here shows the regions of spectral extraction. This magenta feature over here along the rim is actually the X-ray emission from the ROSAT observation. And this box over here shows a region of background spectral extraction. This circle over here shows the field of view of the ARC-CE PCA observation. The yellow boxes show the regions of spectral extraction for the XMM Newton. With this circle here shows the location of that background cluster, and care was taken to excise any kind of X-ray emission from that cluster there. And this shows the regions for the spectral extraction as we perform them. So these features here just try to show the different cuts that we would have. For the soft energy and the hard energy over here is actually going to be panel B, shows the soft emission, C is for a harder cut. These are the two different bands within the within the Rosette PSPC. And D is actually just panel over here is just a two-color comparison, where the soft emission is shown in blue, hard emission is shown in yellow. And in the yellow, you can see that the emission from these harder sources is prominent and becomes significant. Okay, and these are just the point sources here, just labeled once more time for reinforcement for their locations here. Okay. These are the preliminary results of the spectroscopic analysis that we had for this emission. We used components to model the thermal X-ray emission and the non-thermal X-ray emission. We used several different components, standard X-ray emission models to obtain that emission here. So for one was standard model VNEI, standard X-ray thermal emission here, non-equilibrium ionization collisional plasma model. This assumes a constant temperature throughout the region of extraction and assumes a single ionization parameter. This ionization parameter is a product of the number density of the particles which make up the plasma and also the age, if you will, of the plasma, and with variable elemental abundances here. This is one of the most commonly encountered X-ray models for thermal emission. VP shock is a little bit more complex. This one actually tries to say assume different temperatures for the electrons and the ions here, tries to fit them as two different temperatures. The V prefix also indicates that we have variable elemental abundances here too. And finally, the SR cut model. What we would do here is, while in all cases we assumed, in all our fits here, we assumed a thermal model to model the low energy emission from the remnant, we would use either a second thermal component, VNEI or VP shock, to model the higher X-ray emission, or the SR cut model. The SR cut model is a synchrotron-based model. It is with an exponential cutoff to the spectrum here. And the advantage of using the SR cut model is you can draw upon radio observations made of the sort region of interest to determine the flux density at 1 gigahertz and also the spectral index. Using the spectral index and the flux density measured at 1 gigahertz as standard observations and constraining your model, this could return an estimate for the critical frequency at which the spectrum produces the most energy. The electrons which are producing the observed X-ray emission produce the most energy, and from there in turn, you could provide an estimate for what the highest energy particles accelerated by the remnant may be. In this model here shows a fit to the spectrum. And this actually shows the black line is a combination of all the emission which we see here across the for the PCA here, but the other colored lines over here show the emission from all the different components. So we found that the best fit was from a VP shock plus VP shock model over here, and what we could see is, what we could see here was actually just the. Excuse me, I just want to check the time. Thank you. Thanks for the update. What we could see here is actually just the blue here, or this is going to be for the X-ray emission from that hard X-ray source, which is located in the northern rim. That actually had this actually produced the most emission. The background cluster actually will only produce this yellow emission over here. It turned out that the cluster of 3C130 and its own emission over here actually produced significant contributions as well. And the green emission, which you could see drops extremely rapidly, becomes is actually the thermal emission from the remnant, and this drops very quickly. This result is consistent with an interpretation that the hard X-ray emission that's detected from the remnant really does not have to do with anything physically associated with the remnant itself, but more likely originates from any of these other hard X-ray sources which are just serendipitously observed toward the remnant. Okay. But more of our analysis is actually to try to see what the distribution would be of the particles, of the energies of the particles that make up the observed emission. And that's what's shown in this plot over here. This is energy on the x-axis, and this is actually the numbers of particles per a momentum iteration over here. And this is actually showing if you would have for the two components, you'd have for the inner region is shown as a solid line over here. The outer region is shown as a dashed line over here. What we argue is significant is that you actually have the distributions of the energies of the electrons that make up both regions. You have radial variations. We feel that this is an important step forward in analyzing the properties of X-ray emission from these remnants in determining what these properties would be here, how you could have variations in the distributions. So it would show here that if you looked at this is, if we're trying to fit these using a combination of two Maxwell-Boltzmann velocity distributions to fit these spectra over here, what we believe is we're finding evidence is that the distribution is better described with what's called a kappa distribution, which is an alternative distribution for the Maxwell-Boltzmann velocities, or I should say the velocity distribution, than simply a Maxwell-Boltzmann. The kappa distribution uses a power law to actually describe the distribution of the most energetic particles here. And we think that this is actually evidence that if you're having this change in this distribution here, it's showing more that the electrons which are producing emission are coming to more of a thermal equilibration downstream from the shock. We feel that this is an important result in trying to analyze the diffusion and also the interaction particles of the particles which make up the emission along the rim here. Okay, and from the hydrodynamic analysis here is we can actually from a hydrodynamic analysis try to come up with estimates of such key properties as the age of the remnants, the distance, the age of this remnant, distance of the remnant, etc. By using standard models, hydrodynamic analysis, which was pioneered by Truelove and McKee in 1999, and which was applied by Glenn in his analysis of the Vela Junior remnant back in 2015. And if we summarize all this over here, we have the inferred properties of the most probable set of properties for this remnant here. We concur with the estimate that the remnant is located at a distance of 1.8 kiloparsecs and not as nearby as 300 parsecs. The argument for the 300 parsecs was that there was a thought that there might be some absorption seen toward the southern rim by a certain foreground cloud, and which might be interpreted as in some kind of association with that cloud and would be a way to kind of limit the distance of the remnant, but that that result cannot be reconciled with the direct observation of the expansion, the optical expansion of the remnant. We have a radius of 27 parsecs. We have an age of over 23,000 years, and we have age shock velocities, a comparatively lower shock velocity, which can be reconciled with a remnant, with an older remnant like this one here. Okay, proceeding onward here. I'd like to also just talk about in this time here about some results we have for a galactic mixed morphology remnant here. I'd like to ask the moderator approximately how much more time do I have left?
About 5 minutes.
5 minutes? Okay, thank you. I appreciate that. Thank you so much. Okay, so I will, in the last 5 minutes, I will just conclude here with a description of another remnant, CTB1. All of us I know find ourselves working with many projects all at once, and sometimes certain projects show more traction than others. And while I was working on 156, this other remnant I worked on, I've had more traction with that, and I could share some results we have with this remnant here. First, I'd like to talk a little bit about the classification for mixed morphology remnants, such as CTB1, which is over here. While for remnants, the classification of remnants has often been for two main categories, would actually be this ones which are safe or have a center field in the X-ray and the center field in the radio. So morphological classification system, which is based on the morphology of the remnants of the X-ray and the radio. Here you have a center field, the Crab Nebula in both the radio and the X-ray. This is a standard source which we'd have for that morphology. You'd also have for the Cassiopeia A, which actually is shell-like in the radio and shell-like in the X-ray. So it is the excellent example of that class of remnant. But then you also would have the remnants which are center filled in the X-ray, but shell-like in the radio. They have contrasting morphologies here. And the X-ray emission, while there may be in some cases a component which is due to a nebula associated with a central pulsar, neutron star, the central X-ray emission is dominated by thermal emission. And these are called the thermal mixed morphology remnants, or thermal composites. And I could give some example, a prominent example of this remnant here. Excuse me. These remnants with the diffuse X-ray thermal emission, shell-like in the radio, there's still a lot of investigation about why these remnants achieve this morphology. There really isn't a consensus about how these may develop. There may be certainly effects of thermal conduction, which can actually explain this behavior here. So this is a case, for example, of one of the sources here. It's W28. And what I have shown here is a thermal emission, which is from the Rosette HRI, and a overlaid, and I have contours overlaid from radio emission. Remnant has a very strong shell, which is actually most prominent along the west here in the north, but the X-ray emission is localized down toward the center here. And this remnants, mixed morphology remnants, is thought that one reason why you could actually drive this formation is many of these mixed morphology remnants appear to be interacting with molecular clouds. For example, W28, all these cyan crosses here are actually going to be masers, hydroxyl masers. You can see there's a large concentration along this rim over here, but there's other locations over here. So we believe the remnants actually have very strong interactions along this rim over here. And W28, like other mixed morphology remnants, believed to be strongly interacting with its adjacent molecular clouds. So another strong example is IC443, which is also known as a jellyfish remnant. Same situation where you have a radio shell with a center-filled X-ray emission. Studying mixed morphology remnants can also help us understand how remnants and molecular clouds interact with each other. And if we can understand this interaction, this may help us understand why these contrasting morphologies develop. And we can also say that in this era of Chandra and XMM Newton and Suzaku, we find that when we detailed spectroscopic analysis of the X-ray emission from these central plasmas here, realizes a couple of big surprises. The elemental abundances of this X-ray emission are thought to be enhanced. The elemental abundances are more consistent with young remnants which have not entered the seed-off stage here, even though that other estimates of the remnant ages place them that they should be well into the seed-off stage, and their X-ray emission should then be dominated by swept-up material, not stellar ejecta. We also find that a lot of these plasmas are in overionized states. This terms that the temperature that we have, the measure for these, the ionization states of the atoms are greater than what you'd expect just simply on the fitted temperature here. And such a result is thought to indicate a particularly rapid shock heating of the X-ray emitting plasma. Those were two big results there. Okay, let me cut to the chase. Again, with respect to the time and the schedule, I can cut ahead to some of the results we've had for CTB1. Work which was done previously was on an analysis of Asuka and Suzaku and Chandra observations of this remnant here. It's dominated by this curious looking crescent phase of shape over here. And thank you. I'll coming to an end here. It's dominated by this crescent phase of the radio emission over here. The X-ray emission extends outward. The X-ray emission is effectively absent from the southern rim. It's weak from this rim over here. It extends almost like a fountain out from this ridge over here, from this gap. And we found that if we did the fit here, we would find that it would have to be a two thermal components here, which again, a surprise of having two thermal components present at the same time here, but it's maybe evidence that we have complex plasma conditions associated with these remnants, which will produce two thermal components. Okay, I will conclude this talk here for CTB1 by just saying a remarkable result we had with CTB1 in the Chandra data is that we found evidence for oxygen in one of the regions here, which, if established, the detection of oxygen helps clinch that this supernova remnant would have a massive progenitor, which would then become important for trying to classify the stellar progenitor for the source here. The XMM Newton observations are ongoing, where we're trying to investigate the presence of oxygen in the X-ray mission. I'll conclude my talk there. Thank you very much for to the speakers. Thank you very much also to the panel for the invitation, and I welcome any questions.
Thank you, Tom. We can have a short question if there is one. Vladimir, just go on. You can unmute yourself and ask.
Okay, thank you. Very nice talk. Well, my question is about the couple distribution. When you're talking about the couple distribution of particles, of electrons, what are you referring to, non-thermal part or suprothermal and thermal particles?
It would be the non-thermal part. We're exploring this, and I will say at the start that I'm not an expert of it, but it's actually to understand the properties of the electrons which will be producing the highest energy X-ray emission.
That's very interesting because we are getting the same results for the thermal part that we can fit with the couple distribution, but also we think that this non-thermal part is also the sort of couple distribution. So very, very interesting. Thank you.
Yes.
Yeah, if I can interfere, what we see in peak simulations is that you can fit the distribution with the kappa distribution, but when you move down further downstream, it kind of goes into the equilibrium and it becomes Maxwellian. So yes. I'm not sure whether your electrons are in the interior or are they closer to the shock?
That is, we're investigating that. I'd be happy to share a preprint of what we have so far with that. I'd be happy to discuss that in more detail.
Okay. Okay.
Yes. Sure. We could definitely discuss that. I'm interested in getting more feedback and ideas from that as well.
Okay. Thanks, Tom.
Absolutely. Thank you.
Thank you. So let's move further. The next speaker is Professor Dennis Leahy. Dennis, can you hear us?
Yes. Okay, just a second here.
Mm-hmm.
I'll start my share screen.
Okay.
Is that okay now?
It's not in a full screen, but it's okay as far as I'm concerned.
Better?
Okay.
All right. Okay. Right. I'm like to thank all the organizers for inviting me to give this talk. So it's the second talk in a row on supernova remnants. I know a lot of people, that's not their specialty of research. I'll be talking about general properties rather than an individual supernova remnant. It's work I've been doing for a few years at the University of Calgary, mainly with help of undergraduates who are often programmers to help me navigate Python. Okay, so I'll give a brief introduction to supernova and supernova remnants. I'm sure everybody's familiar with this, but just to put things in context, and then go into a review of what are commonly used, or what's the historical background of evolution models, and then describe what I've been doing in the past 5 years up until now. Then talk about the results when we apply these models to large samples of supernova remnants, and we're going to look at both Milky Way samples and LMC. I'm currently working on SMC, but that I don't have anything ready yet. Okay, so just general idea of what supernova are. We know stellar evolution depends on the initial stellar mass, and I'm going to ignore stellar binary evolution for now, just for simplicity. So low mass stars like the sun, well, really low mass stars don't end their lives. They live much longer in the universe, but so roughly 0.5 to almost two solar, well, several solar masses go through the well-known stages of main sequence, red giant, and then end up as a white dwarf. And the timescales depend strongly on the mass. But above, if you get above about 8 solar masses, as during stellar evolution, the nuclear burning goes far enough that the core of the star becomes unstable to collapse. And there's lots of cartoons in the literature. I pulled, sorry, that's this one. I just chose one of them. Where you have an unstable core. The outer part of the star is still in hydrostatic equilibrium, but the time scale for the core is so short. When it loses pressure support, it collapses, and a catastrophic sequence of events follows. This is still an area of research, but it looks like that you form a protoneutron star, and neutrinos escaping from the protoneutron star can reheat the bounce shock from the formation of the protoneutron star and give enough energy to propagate out through the stellar envelope. But that is only in the past 5 years or so that that has happened. And part of it's complex because of the complexities of neutrino transport, which is neither optically thin or optically thick. All right, so the normal stellar evolution doesn't explain type 1a supernova explosions. For that, we need binaries. So that's the thermonuclear explosion of a white dwarf, which requires either to make the white dwarf unstable, heating of the CO core by a mass transfer in a binary, or if you form a pair of white dwarfs, two separate low mass stars which evolve and leave behind white dwarfs, then they could, if their orbit's close enough, they could merge and you get a pair of white dwarfs, and then as they merge, the carbon is ignited basically in the merging object. Okay. Now, this is just a comment that the actual explosion process, this is for a massive star where, I'll go back, sorry. Inside the star, the protoneutron star forms, you have a shock that goes out through these various layers, but the shock propagation is unstable to perturbations and can mix the hydrostatic burning process products of the normal stellar evolution, plus the shock temperature is high enough as you go out from the center. So this is for a 25 solar mass star, that you produce a lot of the elements observed in the universe. In fact, most of the elements produced in the universe are actually produced by the supernova shock, reprocessing the elements produced in the hydrostatic stages of burning. But the shock itself, the instabilities mix all of this. And we've seen pictures of Cas A where any other, well, there's not many supernova remnants where we've observations of the layers of the elements, but they're quite mixed by the shock propagation through the star. From the, when it reaches the surface of the star out into the circumstellar medium, there's less done in terms of hydrostatic simulations, but here's where a lot of simple spherically symmetric models have been done. But the main idea of these is you're a classical massive star, you've got a neutron star left behind in the center and an outward propagating shock, which goes into the circumstellar interstellar medium. But that shock, as it develops, well, first the density is so low that the high density ejecta cools by adiabatic expansion, so you have a cold expanding region. The outer shock is still going out and heating at our stellar medium, but you develop an inward going shock which has to reheat the cold ejecta, which is the stellar envelope, which is expanded and cold. Okay, so I mean, we know all of this. I'm not going to spend time on this. Supernova, we're interested in them because they have big effects on the interstellar medium of galaxies. They produce particle acceleration, the shock front, and we observe the remnants as cosmic rays at the Earth. They're also a lot of the processes in supernova, and well, supernovas are not producing nuclear synthesis products, they're distributing them throughout the ISM. All right, so the interest here is to use supernova remnants as a tool, inputting as much physics as we can to understand the properties of the supernova. Okay, so just a summary of what these models are. The most used model for, if you go to David Green's catalog, most of the supernova remnants there have only had a Sedov model applied, which is extremely simple. So in the history of models, these models were applied to supernova remnants early on, 1972. Radiative losses were realized to be important to give slowing down of the shock and compression of the shell and producing optical radiation from cooling. And later on, the modeling of the ejecta was considered. That it took over about a little over 20 years. So Roger Chevalier developed these similarity solutions, which generalized the Sedov model to allow for ejecta inside the supernova remnant. And for most supernova remnants, they're young enough that the ejecta is important. So I will argue later that including the ejecta, not including the ejecta by using a Sedov-Taylor model gives you quite a bad approximation of the properties of a supernova remnant. Then there were further analytic big improvements to the description of radiative phases of supernova remnants. This was a major paper. There are many other ones as well, but this one particularly outlined well the cooling phases. White and Long realized that if the interstellar medium is inhomogeneous, it could drastically change the evolution. Effectively, what it does is that when the shock first hits the interstellar medium, it propagates through the intercloud medium, which is a low density, gives a fast shock and a high temperature, but over time, cloud evaporation fills the interior with density and homogenizes the brightness and temperature distribution interior to the supernova remnant. Okay, so they found a self-similar solution, but it ignored the ejecta and the radiative phases. Okay, so there's a whole bunch of models which improved description of supernova remnants using numerical models, both for the radiative phase and the Truelove and McKee work, which most people who do supernova remnants are familiar with, introduced this unified evolution, which basically included both the early self-similar phase and what's called the Sedov-Taylor phase, although what's called the Sedov-Taylor phase, I want to argue, is not really Sedov-Taylor. It's really adiabatic, but it's not Sedov-Taylor because the mass of the ejecta has an important effect. And that was realized by Truelove and McKee as well. And there's some other important generalizations, for example, several models which tried to include losses. Motivation was to see how energy loss to cosmic rays affect the evolution of a supernova remnant. Some supernova go off in the hot ISM, and then it would affect their late evolution because of the high pressure of the ISM, which is ignored in standard models. And then later, if you go to full hydrodynamic models, you could do better, but then you can only model one remnant at a time, and you have to guess at all the initial conditions. In the meantime, so these development of all of the improvements of supernova remnant evolution models, plasma emission processes, which were first approximated simply, including various radiative emission processes, free bound, bound free, two photon emission, all of the different atomic emission processes for an optically thin plasma. Other work which put in the complication that the electrons and ions have different temperature distributions. The fact that the electron collisions with the ions only heats them gradually so that the ions won't be, this can take many thousands of years before you could get equilibrium ionization. This is an important thing. And it's included basically in all the X-ray spectral modeling of supernova remnants. So XSpec has been continually updated to include all these modelings. And I think more recently, the one I want to mention here is there's been a good assessment of observations of the electron-ion equilibrization, which I've looked at. And the Cox and Anderson 1982 formula actually does a very good description of the observed TEI over TE evolution. Okay. So I have an evolution, sort of the comments I made along as I went. I've summarized them here. I think that the basic model which you could use to start with is Truelove McKee 99. They include early ejective domination phase and this transition between the ejecta dominated, and I don't know what to call a Sedov-Taylor. Sedov-Taylor may be a good name, but the Sedov-Taylor model is a bad description of it. I don't know if it'll change. In the papers I've published, I've always called it Sedov-Taylor, even though it's not. Okay, so this transition time, the point is that it takes, this is most of the lifetime of the supernova remnant. It's really important. Okay, so back to the Truelove and McKee. In the unified evolution model, before cooling applies, you can put everything in dimensionless form. But it's more complicated because you have to parameterize the ejecta distribution and the CSM distribution. It also assumes spherically symmetric. Trula McKee pointed out that the ejecta-dominated phase, basically, which is the early part, is discovered by Chevalier, and the self-similar models there. It ends when you no longer have you have the reverse shock going in, leaving the power law envelope into the core. And you cannot have a power law envelope all the way into the center because you'd have to have infinite ejecta mass. So that's basically the reason you have to transform from ejecta dominated into this long-lived transition phase. Okay, so the work we've done uses both analytic and hydrodynamic simulations using the Pluto code. And I'll just discuss, as I'm getting on in time here, the basic ingredients of the model. So you can think of it, the first order as Trulove and McKee. This is the Trulove and McKee model here, but to describe it, here's the velocity as a function of radius at a given time in a supernova remnant. In this case, it's 0.492 of the characteristic time, and depending on all the parameters supernova remnant, the characteristic time may be 500 years or 1,000 years. So this is just the Hubble expansion of the ejecta from the star, which is basically given an impulsive velocity as the shock propagates through it, and is cold because it's expanded adiabatically almost to 0 Kelvin. You have the reverse shock propagating inward. So if I had this is the velocity in the observer's frame, but the velocity in the material frame would be inward, and you have the forward shock propagating outward, and this part is shocked interstellar medium, and here's the shocked ejecta. So if you look at the velocities versus time, the outer shock velocity drops with time. The reverse shock velocity also, it speeds up initially, then drops, and then accelerates again. The radius of the forward shock goes out continuing with time, and the reverse shock, the velocity is always inward with respect to the ejecta, but in the observer frame, it's outward at first and then slows down and then propagates in and accelerates and hits the core. Okay, so each different type of ejecta profile gives quite a different reverse shock profiles for velocity and radius, but the forward shocks don't change that much. So I spent a few years putting all of this into a Python code and doing other things like correctly matching the end of the non-radiative evolution to the radiative phase by making sure that the momentum, velocity, and position all match at the transitions, which hadn't been done before. Similarly, matching the White and Long model onto the ejecta-dominated phase by doing proper physical matching and matching the White and Long model onto its radiative phase. Okay, so all of these things were done and put into a calculator. And the other thing we did, which wasn't done in Trulove and McKee, was add the emission measure calculation and a temperature calculation, which is emission weighted temperature, where this is the temperature of the shock material and weighted over the emitting material, which is effectively what you do when you do an observation we also calculated surface brightness profiles. Okay, so this is available as a Python code. I give several windows, including you put in all the parameters. So even though the early stages are described by this unified model, to get the unified model, you have to put in about 10 parameters that describe the ISM and the ejecta and the electron ion heating. Although I've included the Cox and Anderson formula here, so if you don't put anything here, it automatically calculates the electron ion temperature. Okay, you can also do things like get emissivity plots, surface brightness profile plots, and total spectrum. So what we've done since then is improved using hydro simulations. So this is going beyond Truelove and McKee, and going all the way out till we get to the radiative phases, using this Pluto hydrodynamic code and matching all of the hydro results to fitting formula. In this paper, we looked at 15 galactic supernova remnants. And the key thing here is to model a supernova remnant. You need the both the emission measure and the temperatures of the forward and reverse shock material, as well as the radius of the forward shock. All of these can be obtained from X-ray observations, or if you have radio observations for a filled center supernova, you could use a radio to get the forward shock radius. So basically, if you don't have X-ray observations, you really can't determine, not with this code, and I don't think you can with any other code, you can't determine the age or evolutionary state of a supernova remnant. Okay, so in this case, we can apply this model to every single remnant, and we require X-ray observations. And we also require that we have a distance, and there's only, at that time, there were only 15 galactic supernova remnants that had that, well, that we were working with. And also did the same thing with the sample of 60 supernovas in the LMC. We have all the distances and all the X-ray observations. I think that this I maybe skip is just more details of the hydrodynamic simulations. And it shows that, for example, here, this is sometime late that would be normally considered pure set-off, but a pure set-off would drop down like this in the density because it ignores all the effects of the ejecta and the reverse shock going through the ejecta and propagating back out and reheating it. Okay, so the most recent sample was 43 galactic supernovas. This is the entire sample from green, which have distances and X-ray spectra. And we fit, so each remnant, we get a explosion energy and ISM density and an age, and we could fit the cumulative distributions. And as in our previous studies, all of the energies are always log normal. So supernova explosion energies range from 10 to the 49 ergs up to 10 to the 52 ergs with a mean of about 2 times 10 to the 50th. So the 10 to the 51 ergs is a large, significant overestimate of the actual mean of explosion energies. Most are much fainter. And this is actually in agreement with what you'd get if you went to people who observe extragalactic supernova. They would know this, but the supernova remnant community needs to lower the average value they use. And this is consistent with the mean density in the galaxy too, since many of these are outer galaxy supernova remnants. Just look where they are in galactic longitude. Now, a lot of this, I won't go over this anymore. I know I'm just about out of time. Here's the age distribution. And this is showing a large incompleteness because the number drops a lot as you go up in age. We're missing a lot of old supernova remnants, but we're fairly complete, about 10,000 years and younger. And if you look at that, this particular sample gives a birth rate of 1 over 350 years. But if I add in the other 15 supernova remnants from the previous study, I get 1 over 230 years. And if you look at the fraction of the sample surveyed and correct for that, the actual birth rate goes to 1 over 35 years for supernova remnants detected in X-ray. So we've concluded there's no missing supernova remnant if we just use X-ray detected supernova remnants. But that's very biased because in X-rays, we're not measuring all the old supernova remnants, but for young supernova remnants, anything under 10,000 years, we basically see them all. Okay, right, I think I'm out of time here. So there's still improvements that could be worked on the model. So part of this was a bit tedious because the inverse model application is applying this forward model iteratively, but we can do smarter numerical work to make it faster and allow it easier to apply to a big sample. I don't think the data set is going to grow quickly. The biggest possibility to expand this is to revisit LMC and SMC and perhaps M31 and do other samples and just see how different the SNRs in the galaxy and the LMC and SMC are. Okay, right, so one would always bring up the caveat that we're applying spherically symmetric, but when you go to non-spherically symmetric, the problem is how do you break the symmetry without introducing a huge number of parameters. So that's sort of a longer term goal, which may not be achieved for several years. Okay, I'll end there and leave the summary up.
Okay, thank you, Dennis.
Should I stop the share?
You can leave it. We can move on to the questions. Are there any? I can ask a short question about the reverse shock going toward the center, because I know that you were also in Crete at the conference Supernova Remnants, and the people were really surprised. That was my impression, that they were surprised that the reverse shock of Cassiopeia A is moving backwards or standing still from observations by Fesson, I believe. But from the Truelova and McKee model and from your models, you can see that that after a point in time, the reverse shock is actually moving toward the center and not following the forward shock. So
I think it depends.
Why was this a surprise observationally?
Okay, so Cassie is in the stage where, so I mean, in a simple model, you have a constant density core and this power law envelope of the unshocked ejecta, and the reverse shock's moving up this profile. Cassie is already well beyond that. It's because a significant fraction of the ejecta material has been shocked. So it's somewhere here, but it hasn't reached the center. We know there's cold unshocked ejecta in Cassie. Now this is a very simple model because it's 1D, but it didn't surprise me because in this stage, the shock in the observer's coordinates shifts from moving forward to outward to inward, and Cassie should be at the time where it's about the turnaround time.
Mm-hmm.
So relative to the material has a fairly high shock velocity, but proper motions would indicate. So if you measure the velocity from the shock temperature, you get a high velocity, but it's not moving that fast inward in proper motion.
Mm-hmm.
Yeah, I guess I haven't, when I was at the meeting, I didn't discuss that particular point with anyone. I particularly the people who work on Cassie, but I think the people, gee, I'm trying to think who's been doing the hydro simulations on Cassie. I didn't think it was a surprise.
Yeah. Okay. Okay. Thank you.
And you could change the ejecta profile.
Mm-hmm.
Constant density is used for simplicity.
Mm-hmm.
And nobody's really seriously considered other ones, but in reality, the density profile of the stellar core will determine it could be a few different steps on this rather than constant.
Okay. Thank you, Dennis. Thank you once again, and thank you for being here with us. We should move on now to something completely different. So the next speaker is Matija Čuk. Matija, can you hear us?
Yeah, can you hear me?
Yeah. Okay, you can start sharing screen.
All right, let's see. Okay.
Okay.
Let's see. Slideshow. Am I in full screen now?
Yes.
Okay, excellent. All right, I'd like to thank the organizers and thank you for moving me to a kind of more comfortable slot for those of us on the West Coast. And my talk is about something much closer to home and much smaller than we just discussed. So I'll talk about the moons of Mars. So first thing is, what are the moons of Mars? Well, Mars has two small moons, Phobos and Deimos. You can see on top the diagram of their orbits compared to the size of Mars to scale. So Phobos is pretty close to Mars, just several radii away, while Deimos is about 7 radii away. And then also you can see pictures of Phobos and Deimos from spacecraft to scale. So Phobos is about an order of magnitude more massive than Deimos. Now on the bottom you have sideways view of their orbits with their inclinations exaggerated. So there are two things to note here. One is that the orbital planes of Phobos and Deimos are pretty close to the plane of Martian equator. So that's one important thing. And the other important thing is that they're not exactly in the plane of Martian equator. And both of those facts will help us figure out things about their origin. So the origin of Phobos and Deimos has been discussed for a long time, ever since they were discovered. So before 1960s, it was speculated they might be captured asteroids. So they look like asteroids. Mars is close to asteroids. And kind of the best argument is really that they have featureless dark spectra. They look like some kinds of asteroids, but actually since they lack features, it's not a very strong argument. But the argument about them being captured asteroids is completely inconsistent with their orbits. their orbits are in the equatorial plane of Mars. And captured asteroid will have a random orbit. And this has been known for a long time, ever since 1970. So this is kind of a bit of a fact that made it into lots of popular literature, that these are captured asteroids, but actually has gone extinct in the professional literature. So this is a plot in 3D of the orbits of the irregular satellites of Saturn. These are actually captured comets and asteroids. So you can see how their orbital planes are all over the place. They don't care where the equator of Saturn is. So yeah, the most important lesson from this talk, I guess, is that people who work on this don't think that Phobos and Deimos are captured and haven't for a long time. So where do they come from? Well, now the most popular hypothesis is that they are remnants from a giant impact on Mars. When I say giant impact, it's not as big as the one that formed the moon. It ejected much less material, and that's why Phobos and Deimos are much smaller. So interesting thing about giant impact, and pretty much every simulation has found that, is that you eject most of the material not very far. So you can see here on the y-axis the amount of mass in logarithmic scale versus the distance from Mars. And most of the material that is ejected in a giant impact on Mars is within the Roche limit. Within the Roche limit, you only have rings. Outside of the Roche limit, you can have moons. So very little material actually ends up far enough to form moons rather than rings. But that's not the final distribution of material, because once you have all this material orbiting, some of it in moons, some of it in rings, rings and moons would migrate relative to each other. And some of the more distant material might get caught in mid-motion resonances with the larger moons. So things might rearrange themselves a bit. I won't go into detail here. I'll just say that during this rearrangement, different moons would also perturb each other and make their orbits inclined and eccentric, which is not what we see with Phobos and Deimos. Their orbits are close to circular and are close to the equator of Mars. So the crucial link here in connecting this wild early time in the history of Martian moons and what we see now probably has to do with disruption and reaccretion. So if you disrupt moons of Mars, they would form a ring, but then very soon they'll form another moon. And the crucial link between disruption, between impacts and disruption are so-called sesquenary impacts. So for non-planetary people, this might be esoteric, but the impacts on planetary bodies are divided into primary. That's simple. You have an asteroid hitting a planet or a satellite. Then you have secondaries. That is when material ejected from a primary impact goes on suborbital trajectory, a ballistic trajectory, and hits the same body from which it started. You see this on the moon all the time. Around huge craters on the moon, you have splats of material that were ejected and fell back. But especially for satellites of giant planets, but also works for Mars, you have sesquenary, which is Latin for 1.5 order impacts, where material is ejected off the satellite, but it's still orbiting the planet and has a good chance of coming back. And these impacts have higher velocity than they would if they were suborbital. The speed at which sesquenary impacts hit the satellite back depends on how messed up the orbit of the satellite is. If the orbit is circular, ejected from it will be close to circular orbit and will hit back with minimal velocity. But if the orbit of the satellite is eccentric or inclined, not in the plane of the equator, differential precession might make the orbit of the ejecta and the satellite diverge, and they might hit at very high velocities. So the bottom line is, early on, if the orbits of the moons of Mars were excited through mutual interaction, and at the same time there was lots of bombardment from comets and asteroids, they might have reaccreted. So what we are seeing now might not be the first generation of Martian moons. Unfortunately, that means that once you reform the moon, it reforms in a fresh orbit that has no inclination eccentricity. So their present orbits might not tell us everything about their early evolution and formation. But what can we say based on present orbits? Well, so a little bit of theory. If you have a planet that's spinning faster than the moon orbits around it, the tidal distortion of the planet will want to get ahead of the alignment with the satellite. So satellite tries to pull the planet into egg shape. And if there is any water on the surface, like for Earth, water reacts even better than rock to this to tidal forces. And because the planet is rotating fast, the elongation tries to get ahead of the satellite's motion, and that there is a torque on the satellite pulling it forward in its orbit. The net result is that the satellite gains angular momentum and gains orbital distance. So the orbit of the satellite gets bigger while the planet slows down its spin. This is how it works on Earth. Earth-Moon system has expanded by many orders of magnitude since the beginning of the solar system. Also, the moons of Saturn and Jupiter typically move outward because of the fast rotation of those planets. At Mars, it's a bit more complicated because Deimos is actually orbiting slower than Mars is rotating, but Phobos is actually orbiting faster than Mars is rotating. So it rises in the west and sets in the east, unlike all the other orbital bodies. So from the point of view of Mars, so this is in the synodic reference frame, Phobos is moving backwards relative to Deimos. And then when you look at tidal forces, they will pull Phobos backwards against its orbital motion, while they will push Deimos forward in its orbital motion. Remember, these arrows are in the rotating reference frame. In real life, everything is orbiting counterclockwise. So this arrow is forward in the orbital motion, would make Deimos move outward, while the arrow that's slowing down Phobos would make it move closer to Mars. In practice, orbital interaction between Mars and Phobos is much, much greater because of closer distance and also larger mass of Phobos. So we can forget pretty much orbital evolution of Deimos. So Phobos should have moved closer and closer to Mars over the age of the solar system. And during that evolution, it encountered several dynamical resonances with both Mars and the Sun. So here is a picture from an old but excellent paper by Chuck Yoder, where he looked at the different resonances Phobos would encounter. So there are several resonances with the rotation of Mars. So this is 1/2 of the synchronous period when Phobos was orbiting at half of the Mars day. It will get into resonance with features in the gravity field of Mars, which would kick up the eccentricity of Phobos. So the way to think about this plot is that on the x-axis we have same major axis, but time really goes inwards because Phobos is moving inwards. And on the y-axis we have eccentricity, so Phobos gets to the resonance, gets its eccentricity kicked up. Now you have different options for how fast it damps due to tides within Phobos, but it's kicked up again by another resonance with the rotation of Mars, or with a secular resonance with a Martian year, because precession of Phobos at this point will be 2 Martian years. But this kind of explains pretty well why Phobos has eccentricity of a couple of percent. That's because it crossed these resonances with Mars and the Sun on the way in. Similarly, its inclination of about 1 degree can be explained with one of the resonances with the Martian figure. The difference between eccentricity and inclination here is that inclination does not get damped the way eccentricity is. So that's where we were a few years back. There were answers, clear answers to why the orbit of Phobos is what it is, but Deimos caused problems. So the same work I just showed you by Chuck Yoder predicted that the eccentricity of Deimos should be few parts in 10 to the -3, because apart from the resonances with Mars and the Sun, Phobos should cross 1 to 2 resonance with Deimos when their orbital periods were 1 to 2. This should have happened a couple of billion years ago, and it's straightforward to calculate that Deimos should reach eccentricity of 2 times 10 to the minus 3. Now, this looks very small, but it's actually order of magnitude higher than the observed eccentricity of Deimos. To make matters worse, Deimos should have no inclination if it formed from a ring at some point and its inclination really didn't interact with anything else. It should have 0 inclination, but it has inclination about 2 degrees. So we are looking at much lower than expected eccentricity and much higher than expected inclination for Deimos. In the last few years, a new hypothesis has been put forward, and they can explain this discrepancy. So it started with my colleagues at Purdue thinking about the future of Phobos. So since Phobos is moving closer and closer to Mars, at some point, tidal forces of Mars are going to become stronger than the gravity keeping Phobos together, and Phobos is going to be pulled apart in a ring. Maybe it would look a little bit more like a pile of sand being pulled apart than this rock being fractured in the picture, but you get something like that. Then my colleagues thought a little bit about what happens after that. So at Saturn's rings, at the outer edge of the rings, where you have the Roche limit and a little bit outside of it, you have rings and moons coexisting. And when they coexist, rings are perturbed by moons. So this is Daphnis, a small moon of Saturn that lives in a gap very close to the outer edge of the rings, and it's causing these waves in the rings. So the net effect is that when moons cause waves, their orbits expand while the rings themselves shrink. And typically also the moons form on the outer edge of rings. So we can predict that from this ring that forms from Phobos, you might form a new, smaller moon on the outer edge that would move outward while the ring will collapse. But what if the past is like the future? So Hasselberg and Minton, a few years back, proposed that, so now we are here, time 0, and going back in time, maybe there are multiple cycles of ring and moon formation and destruction. So we start with original moons of Mars created in a giant impact. They're all, like all of this is interior to synchronous orbit, which means that in the absence of interaction with rings or other moons, these moons would all collapse onto Mars. Tidal forces would make their orbits shrink and finally fall in. And when I talk about Roche limit, there is a distinction between fluid and rigid. Basically, it means that ring will form moons at certain distance at which separate particles will come together. But once you form a moon, it can withstand higher tidal forces and it can be closer to the planet due to material forces keeping it together than the distance at which it can form. So the moons can form only at this distance, but they can survive, once they form, they can survive closer in. So what happens once the ring is gone, then the moons would move inward. So for much of the history of Mars, you had either moons or rings. So right now we have moon, and there are multiple moons in the past. And during these cycles of moon and ring formation, you always lose mass to the planet. And in between there were rings, and actually most of the time Mars had a ring. And these rings over time got less and less massive. The one strong point of this hypothesis is that all of this dynamical behavior happens closer to Mars than the resonance with Deimos. So that explains why Deimos never experienced the kick in eccentricity that we expect if Phobos started further out. So if you look back at the paper I showed you from Chuck Yoder, his assumption was that you have this evolution track of Phobos here, this little bit, that in the ring-moon hypothesis is very short, but before it was thought to go all the way up and we have crossed the red line, which it shouldn't have. And it also gives us a new explanation for the inclination of Deimos, because the place where the moons form, the place where moons form, the fluid Roche limit is close to 3-to-1 resonance with Deimos. It's much weaker than 2-to-1, but being a resonance of the second order can also affect inclinations. So this is where my own work comes in. Earlier this year, I tried simulating numerically the situation where Protophobos, one of the previous cycles of inner moon, in this case the grandparent of Phobos, just formed from a ring and was still moving outward into the and crossed the resonance with 1-to-3 resonance with Deimos. Now, orbital resonances are quite interesting in being anisotropic. So if you cross the resonance, that is the orbital period ratio, one way you can get capture, and the other way you will never get capture, just a little bit of perturbation at crossing. And to get capture, you need the orbits to converge, which means that the protophobos is moving inwards, which is the opposite direction from the tidal evolution, but can be obtained by having the moon interact with the ring, just like the moons of Saturn interact with its ring and are pushed outwards. So if you assume that there is outward migration of the inner moon at the 1-to-3 resonance with Deimos, you can get capture into the 1-to-3 resonance. So in gray, here is the resonant location with the inner moon, and black is the same major axis of Deimos. So for a while, same major axis of Deimos follows resonance with inner moon. Eccentricity of Deimos here gets excited until the resonance is broken, and here you can see resonant argument for dynamicists. It's actually librating, and here is a secondary resonance that breaks up the primary one. So this secondary resonance is great because it depends on the mass of the inner moon and can tell us how massive it had to be. And we tried a bunch of masses, and since the width of the resonance depends on the mass of the inner moon, the separation between neighboring resonances and the width of the resonance determine when the resonance will break, at which inclination of Deimos. And you can see that less massive inner moons can create more inclined Deimos. We also try different obliquities of Mars. So if we compare these results, so what inclinations we can get with resonances with past inner moons of Mars against the predictions for the masses of past inner moons of Mars from Hasselbrook and Minton, we find that we are talking about something like 2 cycles ago, the grandparent of Phobos. So this would have happened about 3-4 billion years ago. So when there was a moon that was about 20 times more massive than Phobos, which crossed this resonance with Deimos, got Deimos captured in the resonance and inclined, and then afterwards the moon collapsed into Mars, its descendant collapsed into Mars, and its descendant is now Phobos. Now, the 1-to-3 resonance also has the eccentricity component. The eccentricity and inclination components should be symmetric, but we get capture into inclination type resonance, but not eccentricity. And the crucial ingredient is the fact that the sun changes the orbital plane of Deimos and breaks the symmetry between eccentricity and inclination resonances. It's all in the paper. It's in Abjay Letters published earlier this year. But just briefly, we also checked what happens to eccentricity. And eccentricity of Deimos is just kicked a little bit by crossing this resonance twice, because as I said, first the inner moon goes outward and backwards. So you get 2 crossings, but you only get small kicks that give Deimos eccentricity of few times 10⁻⁴, which is what we observe. So the clear implications of this work is that Protophobos, we had a massive Protophobos, that is the massive moon in the place where Phobos is now, and was migrating inward. So to have an inner moon migrate, sorry, we will migrate outward. Sorry for that. To have an inner moon migrate outward, opposite direction of tidal evolution, you have to have a ring. There is no other explanation. So the implications for the ages of the moons is that since we had billions of years ago, we had Deimos around, it had to be a couple of billion years old. But since we had the grandparent of Phobos be around at that time, that means that Phobos is much, much younger. And according to the ring moon theory, only a few hundred millions of years old. If you look at them, they're covered in craters. So those surfaces look geologically old, but the clear consequence is that these craters must have come from planetocentric impactors and cannot be used to determine the absolute age of the surfaces. And we'll know more about Phobos and Deimos in a few years. Japanese Space Agency is preparing Mars Moon Express spacecraft that will image and observe both Phobos and Deimos and should get a sample from Phobos. And maybe there is a way to determine the age of Phobos using the sample through to see how much the material was exposed to cosmic radiation in the past. So here's my summary. So the current thinking is that Phobos and Deimos are a product of a giant impact on Mars. Everybody agrees that early on, probably there were bigger moons of Mars, very close to Mars, that had been very short-lived and fell on Mars very quickly. We find that a few billion years ago, there was an epoch where Mars had both moon and a ring, and interaction between that moon and Deimos generated the present orbital inclination of Deimos. And our conclusions strongly support the cyclic ring moon theory of Hasselbrook and Minton, where Mars had multiple moons and rings over its history. Thank you.
Thank you, Mattia, for a very interesting talk. So, do we have a question? Okay, Zoran, just unmute your microphone and you can ask.
Yeah. Okay. I have a question. Mattia, I would like to say that you are always presenting quite original ideas, but and dynamically what you presented looks, let's say, reasonable, plausible. The problem is, how does it, you say that the rings are lost to the planet, which means that essentially all the debris or all the particles of the rings hitted the planet. How does it fit with the census and the distribution by size of the craters on the Mars?
Yeah, so important thing is that nothing really large makes it to the surface. Through the first through the tidal field, it gets pulled apart into relatively small particles, and then many of them get broken up, falling through the atmosphere. Despite that Martian atmosphere being relatively thin, it still can act in slowing down meteors pretty efficiently. So the amount of mass that fell in varies over time. Early on, the amount of mass was rather large, but we might not be able to observe those deposits since been eroded or resurfaced. For the more recent inflows of material, so the later cycles of moons and rings, as far as the Mars people we worked with are concerned, they think it's consistent with the amount of deposits we have on equatorial regions of Mars. That it would not be a huge, a ridge or something like in the Iapetus, for example. You have a huge ridge; it looks like something fell in. But on Mars, this is not the amount of material that is consistent with deposits on the equator.
Okay, thanks.
Okay, one more question.
Well, It's not a question. I just want to say I really found it really fascinating, your talk. I don't know anything about these things, so but I really actually understood that. Thank you very much. Thanks.
Thank you.
Okay. If there are no more questions, thank you, Mattia, once again, and we can move on to our final lecture for today by Milan Dimitrievich. Milan, can you hear us?
Yes, yes.
Okay, you can start sharing your screen.
Can you see the screen?
Yes.
Well, can I start?
Yes, yes, go on.
Thank you very much. I am very grateful to organizers for giving me possibility to talk about this topic. My talk will be divided. First, introduction, where I will talk a little about applications of stark broadening data in astrophysics, then some basic facts about white dwarfs, methods for calculations of stark broadening data, then applications to white dwarf spectra, and stark broadening parameters needed for such investigations in StarkB database, Serbian Virtual Observatory, and Virtual Atomic and Molecular Data Center. The major applications of stark broadening data are in astrophysics. They can be used for stellar plasma diagnostics to determine electron density and temperature in stellar plasma, then for abundance determinations, for determination of chemical composition of stellar plasma, for stellar spectra modeling, analysis, and synthesis, for chemical stratification. Namely, this is a new field because before, for all analysis, it was normal to take the same abundance across a stellar atmosphere, but now for high resolution spectra, it is often needed to have a distribution of density or abundance of a chemical element across a stellar atmosphere. Also, such data are needed for spectral classification of hot stars, namely for very precise determination of subclasses, because when temperature of star increase, some lines appear and disappear, and looking at the spectrum, you can very easily determine spectral type of a star. Also for monitoring of nuclear processes in stellar interiors, because chemical abundance anomalies depends of production of elements in stellar interiors, and by studying this we can monitor which processes occurs inside the star. Also for radiative transfer through stellar plasma and for determination of stellar opacities. Just as an example, if you want to calculate optical depth, you need absorption coefficient, and in order to calculate absorption coefficient, you need the profile of spectral line, which is broadened due to various reasons, including and stark broadening, and also For example, if you look at the radiative transfer equation, you can see that also absorption coefficients containing spectra line profile enter in such calculation. For example, Perels in a work from 97 worked on a possibility to obtain mass and radius of a neutron star from line profiles, because line profile depends on ratio on mass and radius and also gravitational shift, so that with two measurements you can obtain with high resolution instrument such data. Also, astrophysical plasmas are incomparably various in comparison with laboratory plasma, so that stark broadening may be important for plasma conditions like for neutron stars, which have temperature from 1 million to 10 million kelvins, and atmosphere where dominate highly ionized iron 25, 24, 26, and electron density is there 10 to 22 to 10 to 24 per cubic centimeters. Then you have white dwarfs where stark broadening is of interest, hot stars, up to other extreme conditions. It is of interest also for radio recombination lines. For example, in ionized and neutral molecular clouds with temperatures for 50 kelvins in neutral in hydrogen clouds and around 10,000 in ionized hydrogen clouds, because there for radio recombination line you have observation of lines with principal quantum number of several hundreds, even more than 1,000, and in such case optical electron is very weakly bound with the nucleus, and it is even very small external electric fields can influence on it. And for example, looking at normal stars, this is a graph from a paper which is the principal paper of Master of Science thesis of Sasha Simic. You have here on abscissa spectral types of stars. So Sun is G-type, for example, and these are hotter than the Sun, and you have equivalent with stark broadening and without stark broadening for 38 ionized neodymium lines on average, and you can see that maximal influence of stark broadening is for A-type star and late B-type stars. So if we look at Hertzsprung-Russell diagram, the principal users of stark broadening data are people working with white dwarfs, because there stark broadening practically you cannot perform a good analysis of spectra or abundances without stark broadening. if we look white dwarfs, this will become practically 97% of all stars in our galaxy. White dwarfs with low masses have a helium core, but there are a small amount of such dwarfs because their leaves are in average larger than time interval from Big Bang to now. So the majority of white dwarfs that we observe have a core of carbon and oxygen, and those with large masses, cores of oxygen, neon, and magnesium. Here you can see Sirius B, white dwarf, in comparison with Sirius A and with our sun. So the first 420 Eridani was discovered by William Herschel in 1783, and the second was predicted by Bessel and discovered in 1862 by Alvan Graham Clark. The third, this is one Manen star discovered in 1917. In 1950, 100 was known. In 1999, around 2,000. Sloan Digital Sky, with Sloan Digital Sky survey, the number is 9,000, and now with Gaia, it's over 14,000. So we have considered the amount to study such objects. Traditional divisions is in hydrogen-rich, denoted as dA, and helium-rich dB. Helium-rich have several different types with different temperatures and dominant different spectra. We have now dB can be divided in DO with effective temperatures from 40,000 to 100,000, dB, dQ with carbon lines, dZ with lines of metals, and the coolest can be seen only continuum. In 1979 was discovered a prototype of a new class of these are PG 1159 stars, and they spectra. We see here several spectra with temperatures for 100,000 Kelvin to 140,000 Kelvin. There dominate lines of ionized helium and carbon, nitrogen, and oxygen, all stark broadened with Stark and Doppler effect. And also even hottest stars are discovered, for example, H1504 star with effective temperature of 170,000 degrees. And Dufour and al. Made in 2008 evolution scheme. So a cooling scheme where different types practically with cooling become cooler types. So in order to study such objects, we need stark broadening data. Very often for a very a large number of spectral lines. For example, Patrick Dufour, in order to analyze a new type of white dwarfs with carbon atmosphere, asked for us star broadening data for 1,600 lines. And normally, astronomers, when there is no data, star broadening data for a line, they take 10,000 value of classical value for natural broadening. In his PhD thesis, Christina Jonas writes that up to 2007 in Phoenix code, this is a very good code for modeling of stellar atmospheres, star broadening was calculated using very simple Kurut's formula for 1979, which is really very approximative. So I just want to show you quantum mechanical formula for star broadening using quantum mechanical method, not to enter in details because we have no time for this, but just to compare this and this. And if you want to analyze high resolution spectra, you must use some better methods. So now the quantum mechanical method is not very widely used because of its complexity. Practically the best results are obtained with semi-classical perturbation method, which we use, and you can see that width of spectral lines broadened by star broadening effect is in fact proportional to density of perturber, Maxwell distributions, and sum of cross sections from all possible transitions from initial and final levels, because each such transition practically give a possibility for the excitation and influence on the final width of this transition. So even this formula is relatively complicated to calculate, because you have first of all solve a lot of collisional problems and that integrate all these. So Green in 68 formulated a very approximative approach where all this complicated stuff is estimated empirically from experiments from cross sections, and he introduced this part as Gaunt factor, so that formula become more simpler. But when I started in middle 70s, then Belgrade was practically one of the first centers. Even I can see the first one where star broadening of multiply charged ions was experimentally investigated. And I obtained task to develop some theory to calculate this in order to check the experiments. So if you look at this semi-empirical formula, you can see that you need the exact exactly the same quantity of input parameters as for more complicated semi-classical formula. So first of all, this cannot be applied for complex spectra where there is no enough input parameters for such calculations. And secondly, if you have set for such calculations which is identical to set for semi-classical calculations, then if you use this formula, you just admit that you are not capable to use a better formula and you have all data needed for this. So in this article published exactly 40 years ago, in formula enter only data for quantum, when quantum number for initial and final levels are the same. So only data where delta of principal quantum number is zero or such quantum numbers are equal, and all other perturbing levels where principal quantum number is different are lumped together and estimated with using a virtual perturbing level. Here is given the difference between level of spectral line, initial or final, and this virtual perturbing level. So first of all, the accuracy is approximately the same as accuracy of semi-empirical formula, but it can be applied with less set of data, and also we introduced different Gaun factor using experimental data for cross sections for not only for singly charged ions, but for doubly and triply charged ions, so that this formula can be used also for doubly, triply, and even extend to 4 times and 5 times charged ions, where semi-empirical formula of Green is not applicable. So this is for shift, and we made even a more simple formula when low temperature limit is valid, when this is limit when we have only elastic collisions, so that in this case we can make additional summation, and formula is much simpler. So this is for shift also. So this was modified semi-empirical formula was used in around 500 different works, and semi-classical perturbation results in more than 1,000 different works were used, and we analyzed where it was used. For example, in astrophysics, mainly for abundances determination, for stellar atmospheres, modeling, and different investigation for white dwarfs, A-type stars, and late B-type stars, also for opacities, where it entered in different computer codes, like opal codes, Davros, Rabgal. Also, the second major field is laser-produced plasma and laser for paper dealing with laser-induced breakdown spectroscopy for investigation of laser ablation, also in industry, for design and development of laser, and in industry for laser welding, cutting, and piercing, and also for investigation of radiative properties like transition probabilities, oscillator strengths, radiative lifetimes, emission coefficients, photoabsorption, photoionization, excitation. And also in a number of papers, such data were used for regularities in systematic trends, because we produced a large set of data which is homologous with the same method, with the we can estimate the accuracy, so it's very convenient for such investigations, like investigations on regularities on systematic trends. And I can also note that such investigations are in fact started in Belgrade, and a lot of work was done in Belgrade by Jagoš Purić and his co-workers. Also in this field worked also Nikola Konjević, myself, and a lot of co-workers, for example, Irinel Tapalaga and others. Here is an example of our investigation. Rafik Hamdi, Nevil Ben Nesib, Nenan Milovanović, Luka Popović, myself, and Sibisal Brešo, of influence of stark broadening of silicon cis lines in DO white dwarfs with effective temperatures between 50,000 and 100,000 degrees and logarithm of surface gravity 8. And we can see that in comparison of Doppler, with stark broadening is more important in majority of layers. Here is Rosland optical depth and full width and half intensity maximum, so that we can see that without stark broadening, it is not possible to investigate spectra of white dwarfs. And this is investigation for the same lines for different models with different surface gravity. And we can see this is a line in far UV, wavelength is 1226.7 angstroms, and we can see that with increase of surface gravity, influence of stark broadening dominates, and this influence also dominates with increase of wavelength, so that, for example, in visible or in infrared, this domination is even more present. And we organized our data in database StarkB. It was first developed as Bell data in Belgrade and was online as an international database several years, but after 2002 it becomes impossible to work on it in Belgrade, so I transferred this to Paris, and there obtained immediately informaticians and all needed. And this, for example, you can see the if you want to search data, yellow squares contain data, and if you click on an element, you obtain different ionization stages for which this element, the stark data, exist there. And also you can search Stark B through Serbian Virtual Observatory, because there is a link to Stark B, and this database enabled to us to enter in the first framework 7 project in astronomy, the creation of virtual atomic and molecular data center, which is working, and now I am also in board of directors of this, and Darko Jevremovic is in board of scientific advisory board of this project. So I will finish with this, and thank you for attention.
Thank you, Milan. We can have questions now. Anybody? Okay, if not, thank you, Milan, once again. This closes this final session of today. I would like to thank again all the participants and all the lecturers of today. And if there is an announcement from organizers, I will step down and give you the stage.
Bojan, thank you so much for excellent chairing of this session. I would like to thank also on behalf of organizers to all presenters and panelists presented here. And as organizers, we are announcing the next day of our conference. We are moving to the extragalactic astronomy. You will hear researcher works from the Serbia, across the Republic Croatia, Poland, and we will hear our special guests, full-time Professor Debora Šijački from University of Cambridge, and Professor Mirjana Pović, high-rank official in the government of Ethiopia in Africa, in development of astronomy in Ethiopia, and she was awarded by the Special Prize of the Nature Journal for inspirative work in astronomy. And we will have 2 special sessions dedicated to the gravitational wave universe with 2 guest chairs. Our dear Professor Alexander Zakharov, Institute for Theoretical and Experimental Physics, Moscow, and Professor Žarko Mihajlović from the Faculty of Mathematics. So see you tomorrow. Have a nice evening and all the best. Bye-bye to everyone.
Bye.
Bye.